Hello, my name is Anil Mani and I am a systems engineer working on TI's Fmcw radar, specifically the AWR and the IWR family of devices. This presentation will cover the problem of interference and how it can be managed in TI radars. At the end of this training, you will learn the mechanisms by which interference occurs in Fmcw radars, the different types of interferers, the results of the EU-funded research on mitigating interference called the Mosserim report, and specific methods applicable on TI devices that are useful in avoiding or mitigating interferers. The final section contains a series of high-level approaches towards controlling interference. This section provides an overview of methods to reduce the probability of interference, randomization methods to reduce the effect of interference, and finally methods to detect and repair chirps affected by interference. The application of these methods will help in making your radar robust to interference. We will then end the presentation with some conclusions and references. This diagram represents a typical scenario on a road. Two radar-enabled cars are passing each other. In the past, this was an unlikely event. However, as more and more 77 GHz radar-enabled cars enter the road, the probability of such events become routine. As such, the probability of one radar intermittently interfering with another increases. Such cases of interference can result in a degradation of the noise floor, leading to missed detections, blind spots at certain ranges or directions. It can even, in certain cases, create ghost objects, targets that are seen by the radar but do not exist in real life. Likewise, as more 60 GHz radars are used in industrial settings, similar interference-related artifacts will appear there as well. We begin with a brief introduction to Fmcw radar. In an Fmcw radar system, a chirp, a signal with a linearly ramping frequency, is generated and transmitted. In this alternative plot, we show the instantaneous frequency of the transmitted signal as a function of time. This transmitted signal is reflected from targets in its field of view and received at the receiver. The received signal is a delayed copy of the transmitted signal. The signal received is mixed down using the transmitted signal and then digitized to create ADC data. Since the reflected signal is a delayed version of the transmitted signal, the mixed down signal corresponds to a sinusoid whose frequency is proportional to this delay. Delays can never be negative, so given a positive slope, all valid objects correspond to positive frequencies. With the tone frequency estimated by a Fourier transform, the delay can be estimated. Using the delay and light speed, the distance to the target can be estimated. For more information, please go to the website shown for more training material on Fmcw radars. Before we begin this section, we define two terms. A victim is a radar whose receiver is affected by interference. An aggressor is a radar whose transmit affects the victim's receiver. We begin our discussion of interference with the two different types of interferers, specifically crossing interferers and parallel interferers. In the event that a victim chirp and an aggressor chirp occur in the same time period and traverse the same bandwidth, if their slopes are such that the aggressor's chirp crosses the IF bandwidth of the victim, then we call the aggressor a crossing interferer. In IF, the aggressor chirp's energy is observed as a chirp that rapidly moves through the IF bandwidth. In time domain, the region affected by interference resembles a glitch. Finally, after a Fourier transform is applied on the ADC codeword, in the frequency domain, these crossing interferers typically increase the noise floor. and reduce the SNR of strong targets and bury weak targets, thereby affecting detection and creating momentary blind spots. A final important point to note is that the glitch duration is typically small. It is given by the IF bandwidth divided by the difference in slopes between the aggressor and the victim. For example, if the IF bandwidth is 12 MHz and the difference in slopes is 40 MHz per microsecond, approximately 0.3 microseconds or 4 samples of the final ADC output would be affected by interference. The second kind of interferers are called parallel interferers. They occur when the aggressor chirp and the victim chirp have the same slope. This is likely in a scenario where every radar has been configured with the same chirp. If the delay in the start of a chirp between different radars is within a microsecond or so, the aggressor chirp will be within the IF bandwidth of the entire chirp of the victim. As such, the region of interference is the entire chirp. When mixed down with the transmitted chirp, the parallel interferer becomes a constant frequency tone in the ADC data. After the Fourier transform has been applied on the ADC data, in the Fourier domain, it becomes a ghost object. That is, it behaves like a target at a random distance with a random velocity. Finally, with regard to parallel interferers, there is an important point to note. The probability of a parallel interferer is very small. Interference will only occur if the two radars start nearly simultaneously, such that the aggressor's radar signal is present in the victim radar's IF bandwidth. Otherwise, the aggressor radar signal will be filtered out by the victim's RX. In a typical ultra short range radar with a max distance of 20 meters, the maximum delay of a target is 0.13 microseconds. This limits the IF bandwidth, and interference will only occur if the two radars start within 0.13 microseconds of each other. Having studied the different kinds of interferers, we now move on to methods to mitigate them. We begin with the Mosseri report. Radars in cars are not a new thing, and as such, radar interference has been a concern in automotive safety for a number of years. Still, despite interference, automotive radars are used for many safety of life applications. More Safety for All by Radar Interference Mitigation, or Mosseri, is an EU-funded project to study the problem of interference in automotive radars and recommend methods to mitigate it. It concluded in late 2012. The final recommendations of the Mosseri report are summarized in the next few slides. The recommendations are equally applicable to automotive as well as industrial robotics and represent the best in current approaches to interference mitigation. In this slide, we present a table showing the technique, followed by a brief description of the technique, and then whether it is implementable in TI devices, and finally its usefulness and simplicity. We begin with CFAR-based mitigation. This method simply increases the CFAR threshold, accounting for interference. This decreases the detection sensitivity but avoids spurious side lobes. Is this implementable in a TI device? Yes. The detection threshold for all CFAR routines is user programmable. It is of debatable usefulness because of the decrease in detection sensitivity, but it is very simple to implement. The second method is called dithering in time domain. This method involves dithering the idle time, the time between chirps, or the interframe time, the time between frames. Since this dither is different for the aggressor and the victim, the probability of interference on more than one chirp is reduced. This method is easily implementable in TI devices. A near infinite variation is possible on the idle time. Frames can be generated with dithering as well using software control. This method is very useful, especially for a parallel interferer scenario. It is simple to implement. However, dithering the chirp time may increase noise floor in 2D frame processing. The third method is called direction-specific predefined frequency band separation. In this method, we use a separate band for long-range radar and short-range radar so that they do not interfere with one another. It also recommends the use of a different band for front-facing radar and another band for rear-facing radar. This is easily implementable in TI devices. However, its usefulness is debatable, specifically because cars and robots would turn, especially around intersections, and void this method's usefulness. However, it is very simple to implement and process. The next method involves methods to detect interference and repair ADC data. The region of ADC data affected by interference has to be deduced and repaired. Detection is performed using statistical information of the ADC data. Repairing involves interpolation or signal healing. This method is implementable in TI devices. AWR and IWR devices provide side channel information called chirp quality that aid in narrowing down the region of interference. This is a very useful method for interference mitigation and can be easily implemented on the DSP. The next method is called dithering the phase of each chirp. In this method, we randomize the transmitted phase of each chirp. Since the aggressor would have no notion of this randomized phase, the phase of the interference event would be randomized, spreading the interference across chirps. This is easily implementable in TI devices. Up to 512 random chirps can be configured and used effectively. This is an extremely useful method, especially for parallel interferers. However, the reduction in the interference power level is a function of the number of chirps in one frame. The next method is called digital beamforming. In this method, we place a notch at the direction of the interferer adaptively. This is done by applying a notch filter to the receiver array before processing. The notch filter is applied in the antenna dimension. This is also implementable in TI devices. However, we believe that it may not work well if there are only a limited number of receivers, like 4 or 8. Also, the direction of arrival of the aggressor needs to be estimated a priori. The final two methods are given in this slide. Method 7 involves detecting interference and changing the timing of transmit chirps and off frames. In this method, if an interferer is detected, we avoid it by jumping to a random RF frequency or a random time slot, as shown in this diagram. This is implementable in TI devices and is probably the most useful technique and is reasonably simple to implement. The final method involves specific polarization of antennas. In this method, we use, for example, horizontal polarization for a certain set of antennas and vertical polarization for another set. If an aggressor uses horizontally polarized antennas for transmission and a victim uses vertical polarized antennas for its receiver, then the signal from an aggressor will be severely attenuated at the antenna of the victim. This method requires expertise in antenna design. This is a useful method, but only two different options, vertical and horizontal polarization, are available. Also, this method involves increased complexity in antenna design. Now that we have discussed MOSRIM and found that nearly all of its recommendations can be implemented in TI devices, we will move on to two features that are only available in TI receivers and help in the control and mitigation of interference. The first is the fact that TI receivers use a complex baseband. Receivers that use real basebands cannot filter negative frequency. This has the consequence that the region of interference in a real baseband receiver is double that of the region of interference in a complex baseband receiver. As such, the region affected by interference is doubled due to the fallback from negative frequencies. The fact that TI receivers use a complex baseband has another benefit, that we can look at the negative frequencies and the positive frequencies separately. This allows us to create what we call the signal and image band monitor, which monitors the energy in the positive and negative frequencies separately. When there is no interferer, the energy in the signal band is higher than that of the image band because of the presence of reflected signals from real targets. However, when there is an interferer, there is a sudden spike in energy as the crossing interferer crosses the IF bandwidth of the receiver. This allows us to narrow down the location of the interferer quite precisely, even if the location of interference is not clearly visible in the ADC data. With all the tools and methods that we have seen, we can now formulate high-level approaches towards combating interference. In the next few slides, we describe some methods to avoid, detect, localize, and mitigate interference. These methods include frequency planning with or without synchronization, standardization of chirp designs, synchronization of chirp times, dithering to weaken interferers, sensing and avoiding interference using sense chirps, methods to mitigate interferer damage, methods to reconstruct portions of ADC data damaged by interference. The first method is standardization. Standardization refers to frequency planning and chirp design, as well as time slot management. Frequency planning, based on the resolution requirement, would allow different radars to coexist in different RF bands. For example, the AWR family of devices has 4 GHz of RF bandwidth, which can be divided into two 2 GHz bands and used simultaneously by 2 radars. If a single manufacturer is making all the radars, they can be made so as to be synchronized to the same clock, to a global time for that particular factory. If every radar is then configured with the same kind of chirp and frame, it can result in parallel interferers. However, if every radar's frame is offset approximately 1 microsecond or so to the global time so that they do not interfere with other radars, then a large number of radars can coexist in a limited space and in the same bandwidth. For example, if the chirp time is 100 microseconds and the max distance of interest is 150 meters, that is, the time of transmit is less than 1 microsecond, then approximately 100 such radars can coexist in the same bandwidth. Synchronization would also allow frames to be stacked one after the other so as not to interfere with other radars. For example, if the duty cycle is 10%, then up to 10 radars can coexist in different time slots. Coarse synchronization would be sufficient for the synchronization of frames. The next method involves sensing and avoidance. In the absence of synchronization, we can perform sensing and avoidance. The XWR devices can generate fast chirps of the order of 300 MHz per microsecond. If we keep the transmitter off during the chirp period, the ADC data corresponds to the spectrum. If there were no transmissions by other radars, the spectrum would be silent. The ADC data should only show the thermal noise floor and the noise figure. If, on the other hand, there are transmissions from another radar, we would expect spikes in the ADC data corresponding to the points where the crossing occurs. A max hold of ADC data across chirps would help show the interferer clearly. In the figure, note that the interferer is chirping between frequencies F1 and F2, and hence the ADC output shows energies between F1 and F2. If the period of scanning is long enough to cover multiple frames, we can estimate the number of aggressor radars using the number of discrete bands of frequencies that are used. We can also estimate frame periodicity, bandwidth occupied by chirps, etc. Most importantly, we can find free spectra or time slots where interference-free transmission is possible. The next method involves randomization and dithering. This is most helpful for parallel interferers, which can be further mitigated by this process. There are multiple parameters of a chirp that can be randomized. These include the chirp starting phase, which can be randomized using the per chirp phase shifter API or the binary phase shifter API. The chirp slope, the chirp start frequency, and the chirp idle time can all be randomized using the chirp config API. If no randomization options were used, parallel interferers would appear as ghost objects. If randomization is applied, the peak of the parallel interferer is destroyed by dithering. Randomization works by damaging aggressor coherence across different chirps, thereby reducing their effect during 2D processing. The reduction is approximately 10 log 10 of the number of chirps in one frame. Once the aggressor coherence is destroyed, CFAR algorithms can then be used to weed out interference-related effects. The final method involves localization followed by mitigation. In many cases, it is impossible to avoid a few crossing interferers, no matter what kind of randomization or dithering is performed. In such cases, localization followed by mitigation or signal healing is the best option. Localization refers to the process of finding out which samples in a chirp are affected by interference. This can be accomplished in one of two ways. First, we can find out outliers in ADC data. Strong crossing interferers look like large glitches in ADC data. For example, if you were to take the energy of each sample in a chirp and plot it as a function of time, at the point where the interferer crosses, there will be a large increase in the per sample energy of the chirp. A suitable threshold can be found and set, and samples that cross this threshold in energy can be marked as having been affected by interference. A better method is to use the chirp quality metrics described earlier, like the signal and image band monitor, which is a better alternative for precisely finding interferer locations. Having found the interferer locations, we now would like to mitigate them. Mitigation here refers to the process by which the region of interference is zeroed out and optionally filled in. So the simplest method of mitigation is to replace the region of interference with zeros. That has the side effect of creating large side lobes that might bury weak targets. A better approach is to blank out with a window. A smoothing window is used to zero out the samples that have been affected by interference. This leads to lower side lobes and better detectability of weak targets. An even better approach is to perform linear interpolation in the blanked region, using the last good ADC sample before interference and the first good ADC sample after the period of interference. There are more complex mitigation schemes that are possible. Here, a basic reconstruction scheme is shown. In this scheme, after blanking, an FFT is performed on the blanked ADC signal. The output of the FFT is thresholded so that only peaks that have been unaffected by the blanking procedure are preserved. The thresholded FFT is then subject to an IFFT process, which recreates the ADC data. And this recreated ADC data is used to fill in the blanked region. In this particular example, the reconstructed signal is nearly indistinguishable from the original signal. And we can see that the spectrum after reconstruction shows that the side lobes are well suppressed. This brings us to the end of this presentation. The points to remember are: interference with other radars can cause intermittent issues in FMCW systems. These are typically low probability events, but they need to be handled. Research via Mosarim has provided a set of recommendations to reduce the impact of interference. These can be readily implemented in TI radars. By optimizing chirp design, by using randomization methods, and by implementing localization and mitigation techniques, we can handle moderate levels of interference. The use of chirp quality metrics provided by TI radars can help in localization. Synchronization and standardization options should be explored, as these can minimize the probability of interference even under very dense radar deployment scenarios. And finally, sense and avoid strategies make sense in cases where synchronization or standardization is not possible. For more information, I'd recommend the Moserim report as well as the radar congestion study by the National Highway Traffic Safety Administration. Thank you.